And then I can stop recording if needed.
Hi, Gilberto.
Hello. Hi, Kip.
Hi, Gilberto.
I couldn't tell it was your voice.
Hey, gang.
I had to see the picture. Thank you.
I gotta go check, make sure my son is on his Zoom meeting, so I'll be right back.
Okay. Take your time.
You look very serious, Gilberto.
Thank you.
Very
I hope I don't look too serious.
Yeah.
Every time he's like, you know, doing the AMOS presentation or practicing one, he looked very serious all the time. Hey, Miguel, can you mute your microphone, please? Thank you. So we are looking for Jeff.
Who is?
Who else, Gilberto?
I see 25 participants. I'll have to see.
No. Who is on your committee?
Prasad.
Oh, so Jeff, Prasad,
Kip, yeah.
Kip, and Khan.
That's what I was looking for.
Jeff is in.
Jeff is in, Graham, is that what you said? Oh, I see Jeff now. Thank you.
Howdy. Nice Zoom tie, Gilberto.
Yeah.
Thank you, Jeff.
Yeah, I know there's all sorts of fancy Zoom backgrounds, but I need a Zoom foreground to make it.
You'd be like a paper doll, right?
Exactly.
Hadn't thought of that. That's a good idea.
To wear a green shirt and then have different kind of outfits you can pop on top. And
space suit for you know, SpaceX launch.
Looks like we're waiting for Prasad, and of course we're waiting for Kip to come back, I think.
I'm back.
Oh, he had to go check this. Oh, you're back. Yep. Thanks. All right, so where is Prasad? We will wait one more minute for him.
I think he's already here, Julie.
Sorry, Graham?
He's already here. Look at the participant list.
Prasad, I don't see him. Oh, I didn't realize we were scrolling down further. Okay.
Yeah, I'm here.
Sorry. I didn't realize it went off my screen. So, all right. Well then, welcome to Gilberto's Dissertation Defense. Gilberto has prepared a presentation about 45 minutes, after which we'll allow for general questions. If you want to ask a question during the defense, please raise your hand and I will try to monitor for those. Unless you're a committee member, and then committee members, feel free to interrupt if I don't see your hand. And I will be muting people who are not directly on the committee unless you have your hand raised. So Gilberto, go ahead.
Thank you. Thank you everyone for watching and participating in my dissertation defense. I will be talking about my work on coordination for scalable multiple robot planning under temporal uncertainty. And I want to begin by introducing the theme of first response to natural disasters using multiple heterogeneous robots. So robots have a growing number of capabilities. Robots can fly, swim, and crawl. However, in most real-world scenarios, deploying robots still requires a specialized operator to carefully monitor and control each and every robot action. Scaling such a system is very challenging, and it's very hard to coordinate. So there's this need for a more automated and scalable decision-making and coordination system that allows us to deploy a really large number of heterogeneous robots while coordinating their actions towards a coherent goal. To that end, the goal of this dissertation, when put into a single sentence, is to produce a domain-independent planning approach that scales to multiple heterogeneous robots. Now, when I say domain-independent, I mean an approach that is not custom-tailored to a particular domain or problem, but rather that can be applied to a variety of domains. I've also highlighted the word scales because I want to give you more detail to when I say a planning approach that will scale. And that brings us to the issue of scalability. I have defined scalability as this finite resource that is given by a particular planning approach or algorithm. And this finite scalability resource will constrain multiple planning aspects. And that forces us to trade off across axes while modeling our particular problem. So for example, if you now need to solve a problem and generate a plan that will extend through multiple days as opposed to just a couple of hours, then you have to compromise and either simplify your model complexity, reduce the number of robots, or afford a longer processing time and more computing resources. So the goal of this dissertation is to improve scalability overall and allow us to solve larger problems with more robots and more complex features. In order to achieve that, I will begin by presenting some key background topics. The first one is problem description languages. Now, because we're interested in domain-independent approaches, we need problem description languages that will function as the interface between those domain-independent methods and the specific domain details that we are interested in solving. Problem description languages allow us to model how the robots interact with the real world. So for example, if you're modeling a problem where autonomous robot trucks need to move from one location to another location, you could describe a drive action that will have a set of conditions that must be true before this action is executed. So for example, the robot must begin at the origin and there must be a road connecting the two locations. And actions will also have effects, which become true once the action execution is completed. Now, problem description languages can also incorporate more advanced features that allow us to more accurately model the real world. For example, durative actions allow us to model the fact that different actions take different amounts of time to complete. One extension to that, uncertain action durations, allow us to go even further and model the fact that there is uncertainty in the real world. And instead of having a deterministic action duration, we can have a probability distribution over time. Now, all those more advanced features bring us back to the issue of scalability. And this is because with the existing planning methods, as you increase the model complexity with those more advanced scalability, more advanced features, you end up having to compromise somewhere and simplify your model by reducing the number of robots or simply affording a longer processing time. So once again, our goal is to produce this domain-dependent planning approach that will scale and improve, not only include more advanced features, but also allow us to scale to a larger number of robots and resolve problems faster with less computing resources. So,
hey, Gilberto, sorry, I still don't quite understand this figure. So the dashed line, what does that represent?
Oh, I see. So this is to represent the fact that since we're providing domain-independent approaches, we're not particularly constraining how you should distribute, how you should model your problem, right? So for example, if you're modeling a logistics problem, or if you're modeling a first response problem, or if you're modeling some other type of multi-robot problem, you get to use the problem description language to specify how many robots you want to have, how complex each robot model should be. And so by modeling your problem, you get to decide how to distribute across these axes. However, any given algorithm or planning method will constrain the overall area of this shape. So the dotted line means that when you change your model, yes, you can trade off across these axes, but because the existing algorithms constrain your overall scalability, you have to trade off and compromise. And you need to say, reduce your time horizon in order to increase your number of robots and so on.
Got it. Thank you.
Thank you. And so because we have this limited scalability, this dissertation has leveraged and also built upon existing concepts from multi-agent literature. The first of them is multi-agent plan synthesis. In multi-agent plan synthesis, instead of solving the planning problem as a monolithic problem, agents will get together and coordinate how to factor this problem into smaller problems, into smaller tasks. And then agents or robots can independently synthesize plans for those individual tasks. And ultimately, those agents or robots will get together again and coordinate to merge their plans into a global coherent plan to make sure that there are no conflicts between those individually generated plans. Now, one type of approach that incorporates the multi-agent plan synthesis is the coalition formation and planning framework. Now, the coalition formation and planning framework has many sub-processes, as you can see. However, I just want to focus on 3 key processes. The first is coalition formation, which employs existing coalition formation algorithms from literature that will consider the robot capabilities, divide the robots into coalitions, and then allocate them tasks. Then those robot coalitions can individually plan for those tasks and ultimately merge the individually generated plans into a global coherent plan. Now, one limitation with the existing framework is that the coalition formation algorithms rely in a simple model of what the robots are capable of, and normally don't take into account all the details of the planning domain models. Because of that, one existing enhancement to the framework was to introduce the task fusion process, which looks into the coalitions and tries to decide how can it change those coalitions and fuse them into larger coalitions in an attempt to improve the overall scalability of the system by reducing the computational complexity. However, this existing method of task fusion has relied upon very simple heuristics that also use the simple capabilities model from the coalition formation algorithms. And thus, it failed to result in a more scalable overall system. Now, I want to move on to summarize to outline what's coming up next, which are the key developments of this dissertation. The first is task fusion, which contributed to better robot coordination before planning. The second is plan merging, which contributed to better coordination after planning. And the last is a multi-robot coordination system that allowed us to deploy the entire system in a real-world multiple robot setting. So I want to begin by task fusion. And since I've already presented in deep detail this research direction during my prelim, I will focus most of this talk in the later developments which relate to plan merging. So going through the task fusion developments, as I said before, task fusion attempts to improve the overall coalition formation and planning framework by looking into the individual coalitions to fuse them into larger coalitions. However, again, the existing heuristics have resulted in limited benefits. So this research direction on this dissertation has looked into this problem and realized that by using different heuristics, more accurate heuristics, we can, in fact, improve the overall system scalability by reducing its computational cost. However, in order to achieve that, we had to introduce a new family of heuristics. Those heuristics, instead of relying on the coalition formation models or in other simple aspects, it actually leverages the planning domain model and uses this planning domain model to try to estimate coupling between individual tasks. By estimating coupling, these new heuristics fuse the individual tasks into larger tasks and larger coalitions, thus improving the overall system scalability by reducing its problem complexity. Now, I want to move on to focus on the most recent developments of this dissertation, as Task Fusion has contributed to coordination before planning. And now this later part of the talk will focus on coordination after planning. Before I get into the details of that, I want to emphasize again that domains such as the first response domain involve situations that are very dynamic and very uncertain. So for example, when sending a robot out to rescue a victim, it's very difficult to predict the exact time it will take to execute each robot action. So such domains require us to account for the fact that we have a vague probabilistic estimate of how long those actions will take. And so it's important to accommodate for advanced features such as uncertain action durations. Because of that, this dissertation has introduced the Maple language, which is a problem description language that extends an existing single robot problem description language in order to incorporate a model of capabilities, multiple robots, and thus make the coalition formation and planning framework be supportive of uncertain action durations. Now, all of those advanced features, they add more strain in the overall system scalability, as I said before, and especially plane merging. Since the existing algorithms for plane merging, they either cannot scale because they are too complex and they try to eliminate redundant actions and perform other tasks, or they simply do not account for the action durations and they fail to minimize what we call make span, which is the overall plan execution duration. So to that end, this dissertation has introduced 3 new, more scalable plane merging algorithms that remove or mitigate the bottleneck imposed by coordination after planning in the form of plane merging. The first of them, the serial algorithm, is more of a baseline plane merging algorithm that performs simple task concatenation and forces the tasks to execute serially in the same order in which they were synthesized. Now, this is a very simple and fast algorithm. However, it results in very long make spans. The other algorithm, the solution test algorithm, or STA, was extracted from a much larger algorithm that attempted to remove redundant actions, but failed to even scale to a handful of tasks. So the STA was repurposed to perform simple plane merging more scalably. And the STA does so by performing an iterative conflict resolution when it tries to resolve conflicts between individual multi-agent plans. It does so by means of a constraint satisfaction search that will simply return the first viable plan encountered. Now, the STA does not account for action durations, and it also does not minimize the resulting make span. And because of that, the last plan merging algorithm introduced was the temporal optimal conflict resolution algorithm, or TCRA star. The TCRA star also performs an iterative conflict resolution. However, it does so by employing an A-star search. This directly minimizes the make span and offers formal quality guarantees. The way the TCRA star operates is by sorting its internal search queue by using a plan cost estimate that is composed of the current plan's make span plus an admissible heuristic multiplied by an epsilon greedy relaxation scalar. This overall cost gives us an estimate of the final plan's make span after all of its conflicts have been resolved. And the epsilon greedy relaxation scalar allows us to tune the level of greediness of this A-star search. Now, those 3 algorithms perform plane merging at a high level. However, they rely on low-level algorithms and assumptions in order to identify and resolve those individual conflicts. One contribution of this dissertation was to further look into those low-level assumptions and try to understand how they impact the overall plane merging algorithm and limit its scalability. So I will present now in detail how those different assumptions and how those individual conflict identification algorithms and resolution algorithms can impact the overall system. And I want to begin by presenting you with an example plan. In this plan, the actions are represented by the ellipses, and the temporal constraints between the actions, the temporal orders, are represented by the arrows. Now, as I said before, individual plan actions have conditions which must be true before the actions are executed, and they also have effects which become true after the action execution is completed. Now, I want to begin by showing a very simple example in a first response domain where one robot has planned to rescue a victim, but because it does not have built-in lights, it needs to locate the light switch in an indoor environment, turn on the lights so that it can then rescue a victim. Now, another robot in the same environment has generated a plan to detect gas leaks. However, this other robot needs a special sensor that requires the lights to be off in order to detect the gas leaks. So this other robot has planned to locate the same switch, turn the lights off, and then find gas leaks. Now, while merging those individually generated plans, there are two types of conflicts that the merging algorithms may encounter. Assume that we're in the process of merging those two plans. The first type of conflict that we might encounter is what we call open preconditions. Open preconditions happen when the conditions of a particular action are not satisfied by another action's effects. In order to resolve an open precondition, the algorithms need to encounter an action whose effects satisfy that condition, and then introduce a temporal order, such as the one represented by the red arrow, that will enforce that ordering between those actions, thus creating a causal relationship between those two actions that will satisfy the conditions. Now, the other type of conflict that we might encounter is what we call causal conflicts. In causal conflicts, there already is a causal relationship between two actions, as you see in the bottom. However, there is another action, as the action on the top, whose effects deny this causal relationship and may threaten its success. And this happens because the action in the top is not ordered to happen before or after the actions in the bottom, thus making it possible for the lights off action in the top to happen simultaneously with the victim rescue task, thus jeopardizing its success. Now, causal conflicts are a little more complicated than open preconditions, and they require some built-in assumptions as to what qualifies as a solution to a particular conflict. Because of that, one contribution of this dissertation was to clarify those assumptions and establish two separate models that embed the assumptions that can be made while identifying and resolving causal conflicts. The first model, the direct model, requires a solution to introduce a causal order directly between the actions involved, as you see represented by the red line, the red arrow. The other model, the transitive model, not only accepts a direct ordering separating the actions involved, but also an indirect order, as you see represented by the shorter red arrow. This indirect order can leverage an intermediary action to solve the conflict, enforcing the fact that the lights off action should happen before the lights are turned on again to rescue the victim. Now, the key differences between those two models towards the overall plan merging complexity and the overall planning scalability is that the direct model, as it is more restrictive, results in fewer possible solutions to any individual conflict, thus reducing the branching factor of the plan merging algorithms and minimizing their overall complexity, improving their scalability. Whereas the transitive model allows more alternative solutions, however, it can negatively impact the system scalability overall. Now, another concept that is important towards improving the overall system scalability is the employment of the transitive closure. Now, the transitive closure is a standard procedure in graph algorithms, and I want to introduce it briefly using an example. Imagine we have this simple plan on the screen. The action on the left is indirectly ordered to occur before the action on the bottom, both of the actions highlighted. Now, there's no direct ordering separating those two actions. There's only a indirect ordering. The transitive closure algorithms will identify this implicit ordering and will introduce a direct order between those two actions, as you see highlighted by the red line. And it will do so for every implicit ordering. Now, the importance of the transitive closure to improving the overall plan merging performance is that a large number of different plans, while trying to identify a valid plan, they're actually transitively redundant. What does that mean? It means that when we apply the transitive closure to any of these plans, they become the same plan. So the transitive closure can have this funneling effect on the space of plans, thus minimizing the overall plan search space and improving those algorithms' complexity and improving their scalability. Now, I want to summarize all the concepts that I've just introduced here. And I want to begin by summarizing the 3 high-level plan merging algorithms that can be more scalable. Those are the serial algorithm, the SDA, and the TCRA star. Those 3 algorithms, they perform high-level plan merging, which, once again, I just want to emphasize that is a form of coordination after planning. Now, I've also introduced the conflict models, the direct and the transitive conflict models, and the transitive closure, all of which are supportive of those high-level plan merging algorithms, and they're actually building blocks of them, and they can have a profound impact on their overall performance, and thus reduce the overall, improve the overall system scalability. Now, the relationship between those algorithms and those models is very complex, and there can be emerging behaviors. Because of that, we've performed experiments across multiple domains, evaluating the combinations of those algorithms with those models with and without the transitive closure. The domains that we evaluated them on were the logistics domain, where different types of autonomous robot trucks need to exchange cargo in order to deliver them across a connected road network. The blocks world domain requires different robot arm types to stack and unstack blocks from different stacking configurations. And the first response domain requires different types of robots to coordinate while rescuing victims, collecting hazardous materials, and resolving all other types of first response tasks. Now, those 3 domains were enhanced to support uncertain action durations and more robustly represent the complexities of the real world. We have generated random problems across 1 to 10 tasks and 2 to 10 agents, and evaluated the 3 high-level merging algorithms, the serial, the STA, and the TCRA star. The TCRA star with an epsilon greedy value ranging from 0 to 100. Those 3 algorithms were evaluated for the 2 conflict models, with and without the transitive closure, and each problem instance was allowed a limited amount of time and memory usage to complete. The metrics evaluated were the success rates, which represent the percentage of problems that were successfully resolved within the time limits, and indirectly represents the overall system scalability to a larger number of tasks and robots. And the other metric evaluated was the make span, which once again results from the overall plan execution duration in minutes and represents the plan quality. Now, I want to begin by walking you through the results in the logistics domain, in this case here for 2 robots. And we're looking at the success rates. So notice that that ranges from 0 to 100%, and it goes from 1 to 10 tasks. The first thing to notice here, as we look at the STA, this is the STA algorithm results with the direct model with and without closure, and the transitive model with and without closure. The first pattern that we noticed that also occurred across all problem instances was that as we increase the number of tasks, the success tend to drop, which is not surprising. We also noticed that the direct model with closure had the highest success, whereas the transitive model was significantly worse. Now, another pattern that we notice is that when we move from 2 robots in this plot to now 4 robots and more robots, we notice that the success rates tend to increase. And this is a pattern that we observed overall. Now, moving on to the TCI star results, we're looking at TCI star with an epsilon value of 1 and 2 robots. First thing to notice is that we also have that pattern where the success decreases with the number of tasks. However, we see an overall lower success rates for the TCI star. This happens because the TCI star offers formal quality guarantees and results in a more thorough search in the space of plans, thus reducing the overall success rates. However, we see a similar pattern in that the direct model with closure resulted in the highest success rates. And also, as we increase the number of robots from 2 robots to 4 robots, we have an overall increasing success. Now, when we look at the makespan results, and I want you to please take the time to notice that we've grouped all the TCI star instances and the STA with the direct model with and without closure into the same line, as they all resulted in the same average makespans, which also happened to be the best makespan represented by the red line. Whereas the STA with the transitive model with and without closure was slightly worse, and the serial algorithm was the worst of them. And this is for 2 robots. However, as we increase the number of robots and we move from 2 robots to, say, 10 robots, we notice that the serial algorithm tends to grow worse in terms of makespan, whereas the STA and the TCI star tend to actually minimize the overall makespan. And this happens because both the STA and the TCRA, differently from the serial algorithm, they actually resolve conflicts and give the added robots the chance to more simultaneously execute their actions, thus minimizing the resulting makespan. Now, when we move on to the blocks world domain, I wanted to also please note that we changed the plotting format here. And this is because in the blocks world domain, most algorithm instances resulted in 100% or near 100% success. So I'm showing you here some of the few instances where we had significantly different from 100% success. So we're looking at the STA and the TCI star using the direct model without closure. And the TCI star is being presented for an epsilon value of 0 and an epsilon value of 1. Now, as you can see, the TCI star with an epsilon value of 0 has significantly lower success. And this was noted across all domains, as the TCI star with an epsilon value of 0 eliminates the heuristic, thus making the TCI star equal to a uniform cost search, which is very costly and does not scale. Now, when we move on to the blocks world makespan results, we notice a very similar pattern to what we've already seen in the logistics domain, where all TCI star instances and the STA with the direct model with and without closure resulted in the best makespan. Now, moving on to the first response domain, here we're looking at the first response success for STA in the same format as we've seen before in the logistics domain. We noticed that the highest success rates were also provided by the direct model with closure. So we also see similar patterns to what we already saw in the logistics domain. And when we move to the TCI star algorithm, again, similar patterns in that the higher number of tasks reduces the success. However, the added robots improve the success. Now, moving on to the last set of results in this portion of the talk, we're looking at the first response makespan with 10 robots. And once again, it's a similar pattern to what we saw in that the TCI star, all of its instances produce strictly the best makespan, whereas the serial algorithm is the worst. Now, the takeaways from this are that first, the direct model and the closure, they both improved the overall TCRA and STA success, in that they improved the success rates, thus they improved the scalability of the system, and they also resulted in higher quality plans, producing plans that have a lower make span and take less time to complete, to execute. Now this happens because the direct model results in fewer conflict solutions identified per conflict, thus reducing the branching factor of those searching algorithms. Whereas the transitive closure funnels the overall planned search space. Now, both the STA and the TCRA star, they leveraged the additional robots, as the more robots that were added gave them more leeway to simultaneously execute their actions. The TCRA star, as it offers formal quality guarantees, also functions as a benchmark for plan merging quality, as it optimally minimizes the resulting make span. Now, I want to move on to the last part of this talk, which relates to how we developed the system that allowed us to deploy this overall framework in a real-world scenario, in a real-world multiple robot system. And I want to do so by presenting a video. So in this video, we show a first response domain scenario that we emulated with physical robots. And in this scenario, we had 2 rescuer robots, 2 ambulance robots, and 2 hazard collector robots that were supposed to solve 2 victim rescue tasks and 2 hazard collection tasks. Now, the victim rescue tasks required the rescuer robot to move to where the victim is located and perform a clearing behavior to make sure that this area is clear and safe before the arrival of the ambulance, which will then arrive there to load the victim and then transport this victim to a safe location or hospital and unload the victim. Now, the hazard collection tasks are similar in that they require the rescuer to cooperate with a hazard collector robot to collect hazardous materials and bring them to a safe location. Now, in this demo, the ambulances were allocated to each of the victim rescue tasks, the hazard collector robots were allocated to each of the hazard collection tasks, and the rescuer robots were allocated 2 tasks each. Now, the tasks were individually generated for, the plans were individually generated for each task, and ultimately they were merged into a global coherent plan by resolving conflicts and employing the plan merging algorithms that we talked about before. Now, the example plan that you see here was merged by the TCRA star algorithm, which, as I said, it optimally minimizes the resulting make span, thus allowing the robots to more simultaneously execute their individual task actions. Now we see the robots beginning their plan execution from their rescue base. The first thing that we will notice is that both rescuers, they begin executing their tasks simultaneously, and they move forward to begin their clearing up actions to make sure that the victim locations are safe before the arrival of the ambulances. Now, once they're done with that, they will allow all the ambulances and all the hazard collectors to move forward with executing their tasks simultaneously. Now, one downside of the TCRA star algorithm is that it favors simultaneous action execution. And this makes it more likely that robots will collide against each other as they have limited sensors. Now we see them returning to their rescue base after completing their tasks. Now, getting back to these slides, we have performed 1,000 simulations and 10 real-world experiments on this emulated first response domain. And we experimented with the 3 plan merging algorithms, the serial, the STA, and the TCRA star. The TCRA star using an epsilon greedy value of 1. And those plan merging algorithms were evaluated for the 2 conflict models with and without the transitive closure. And they were also evaluated with and without a safety policy, which we developed to allow the robots to communicate to each other and avoid crowded locations to minimize collisions. Now, before we start looking into the details of the aggregated results, I just want to emphasize that those results relate to the make span. So this is the overall plan execution duration in minutes. We also like to note that the error bars represent the standard deviations. The blue bars represent the simulated results, and the real world results are the orange and green bars, which represent the safety policy off and the safety policy on. Now, the first thing to notice is that all TCRA star instances, in addition to the STA using the direct model, resulted in the same plan, which produced the lowest make span across the simulated and the real world results. Now, the STA using the transitive model, both with and without closure, they resulted in intermediary make spans, whereas the serial algorithm, as we expected, was the worst. Now, a few other things to notice here in this plot is that the simulated results were consistently faster than the real world results. And this happens because the real world robots, they actually perform some level of collision avoidance that tends to slow down the overall plan execution. Now, the takeaways are that the real world and the simulated results align and support each other. The TCRA star algorithm, as it offers formal quality guarantees, resulted in the best make span across all of its instances. So with the direct and the transitive model, with and without closure. Whereas the STA instances had make spans that varied, as its constraint satisfaction search does not offer quality guarantees and may result in worse make spans. Now, the serial algorithm, as we expected, was the worst overall, as it forces the actions to execute serially, the same order in which they were synthesized. Now, I want to move on to summarize the contributions of this dissertation. And I want to begin by stepping back and giving us a more broader overview of what the long-term goals are. So our long-term goals are to allow multiple robot deployments in complex real-world domains. Now, to that end, as I emphasized before, we need to incorporate for more advanced features that more accurately model the complexities of the real world. This dissertation has addressed parallel and asynchronous action execution with durative actions and uncertain action durations. Now, there will be in the future more challenges to be overcome, and we will need eventually to incorporate to address uncertain action outcomes to allow for contingent plans and partial observability to allow for information gathering actions. Now, the primary contributions of this dissertation were, first, the task fusion heuristics that improved coordination before planning, allowing for higher quality plans to be generated at a lower computational cost, thus improving the overall coalition formation and planning framework scalability. The plan merging algorithms that allowed us for merging plans with uncertain action durations and durative actions more scalably than the existing algorithms. And also the conflict resolution methods and approaches that are the building blocks towards plan merging and have a key impact in the overall plan merging computational cost and can improve the overall scalability of the system. Now, on the way towards accomplishing those primary contributions, a few secondary contributions were also achieved. Those secondary contributions include the Maple language, which allowed us to extend the coalition formation and planning framework to support uncertain action durations. The multiple robot coordination system, which allowed us to deploy this whole framework into a real-world physical robot system and evaluate the different algorithms that were proposed in a real-world setting. And ultimately, all the software developed will be made open source to allow other research groups to replicate our results and build upon them. Now, I would like to thank primarily my advisor, who supported me throughout all those years. I would also like to thank the committee for their patience. And I would also like to thank the undergraduate students who have contributed to this work across the past few years, Miguel and Ziad. And ultimately, I'd like to thank my friends and colleagues who have provided me with their insightful and constructive feedback. Thank you all. Questions?
Thank you, Gilberto. Well,
Thank you, Julie.
yeah, Jeff put up a little clap symbol.
Thank you, Jeff.
It's hard to clap on Zoom.
Yeah.
So we'll move to the open question period. Does anybody have any questions they'd like to ask? You can use the hand raising mechanism if you'd like. Committee members?
I told the students that they need to ask more questions in the open session and exams. So let's see if they listen to me.
Okay.
I don't see any hand raising.
I see Seth raise his hand.
Go ahead, Seth.
All right, and just for everybody that was like me, that was spending time looking for the raise hand thing, it's under the participants tab in Zoom.
So click on your own name and then you can raise your hand.
So my question for you, Gilberto, is your major contributions are like a pre-processing step and post-processing step to this sort of general like task allocation algorithm. Is there anything that you found during your work that where it seemed to matter what was going on in that middle step, or is it just sort of completely agnostic?
So that's an excellent question. So this overall process, so there are many ways to approach this multi-agent plan synthesis process, right? So coalition formation and planning is one solid framework to do that. The good thing about those modules is that you can transfer them to other approaches. So for example, the plan merging step, it is not only applicable to the coalition formation and planning framework, but any kind of distributed plan generation that you may have for robots, right? So you could combine, you could use something else for task allocation and then use the plan merging algorithms and vice versa. Now, to address your question, yes, improving the key planning in and of itself is kind of like an orthogonal line of research, right? However, by kind of circumnavigating, it's like going around that, we can actually improve the overall system performance using the existing planning algorithms that are already out there. And so the other good thing about this approach is that we can actually leverage those algorithms. So for example, these algorithms, they incorporate for many different features, like I said, right? However, if you just use them as a monolithic system, they can be very slow. So when you put them into this framework and then you do better coordination before and after planning, you actually use them as better building blocks towards a much more scalable system. So yes, there is research into just the planning part. However, that's orthogonal. It's kind of like we're building off of each other, right? So like they can make their part more scalable, but by making our part more scalable, we're kind of building together. So
I guess my question was more along the lines of did you find that specific planning algorithms that you could use sort of provided outputs where your stuff was more efficient, or you had to do sort of less processing to achieve the same results?
Yes, that's an excellent question. So so we actually looked into that in detail while developing the task fusion algorithms. And we done that because back then we were not incorporating for uncertain action duration. So there's a much larger set of existing planning algorithms that suffice when you don't need those more advanced features. However, when you need to include those more advanced features, such as uncertain action durations, then you start to run out of options, right? So back then, when we did look into that, we did notice that different algorithms, they would behave differently when you put them into this framework. However, their interactions with the task allocation and merging are very complex. A good future work would be to actually try to understand how they interact together. But it's still kind of an emergent behavior. When you put, say, a completely different type of planning algorithm in this framework, and then you swap out for another algorithm, they kind of converge towards something that is a bit emergent. We don't actually have a good model to predict and say this algorithm will behave this way, but this other algorithm will behave in a different way. So some of them do better in this environment.
All right, thanks.
Thank you.
Other questions?
So I have one that I think be interested in having everybody hear the answer. So when so you do the experiments, you have that graph where the trends are the same, but the sort of the magnitude is a little bit different. What is it that is different about the robot trials? What are you gaining from doing the robot trials versus just doing the simulations?
I see. Yeah. So the key thing that we gain is that there are unknown unknowns, right? So when you have all those algorithms running simulation, it's great. However, it's important to actually deploy them in the real world, because there can be factors that we simply do not know that they can happen. So when we deploy and we actually experiment in the real world robots, we reveal that either, hey, there are things that we never thought of in simulation, and they can actually impact the overall system performance, or we can conclude that they behave pretty much the same. Now, that's usually not the case. So as we saw, because the robots, when we deployed, they were actually avoiding collisions, and that was not in the models, that resulted in a overall longer make span. So it's that kind of unknown unknowns that we're looking for when we deploy those algorithms in the real world, to try to see how will they actually behave? So that's why I think it's important to actually try them out in the physical robot systems.
So I think, the collision avoidance might be more of a known unknown. Like, you kind of knew that was going to change things because they were colliding. So what were some other things that you learned, that from the real world experiments that really surprised you? Was there anything?
Yeah. So one of the things is that so obviously, so this was a bit of an emulated domain, right? So we were not actually having them go and rescue real victims. I'm sure that once we move to that step and we have robots that are actually capable of loading a victim into an ambulance, we will have a much richer learning experience where we will realize things that we never thought of. However, in this more controlled environment, the real surprises were how difficult it is to actually put a system that we consider resolved, right? So for example, we think of low-level path planning and obstacle avoidance as resolved problems. They're actually not. And they actually make the deployment process a lot more complicated, because suddenly the robots are not converging towards where they're supposed to localize. They don't know where they are, or they're spinning out of control. So there are all those random things that we think we know, and we think they are controlled for, and we think they're going to behave the way they're supposed to, but they end up not. So there were many robot related things, especially for aspects that we take for granted, like low level path planning or simple obstacle avoidance, that end up changing the overall system behavior.
Related to that question, Gilberto, can you say a little bit about the ability of others to use that architecture you showed briefly on one of your prior slides?
Yeah, so the other good thing about this architecture is that it's not just for plane merging research. So this architecture, it can actually, I think it's on the conclusion slides. I had a summary of this architecture right here. Okay, so using the same framework, which is very general, we can actually evaluate many different types of robot behavior. So for example, we could have learning algorithms that will use reinforcement learning to devise their policies as opposed to traditional planning. And using this general architecture where the robots are simply deciding what they want to do and then communicating to others at a high level, we can actually evaluate a variety of other type of algorithms, and not just planning and not just task allocation.
Other questions? Well, if no one really has any other questions, then is there, oh, go ahead, Seth.
So it looks like the sort of framework that you've developed is intended to be sort of a one-shot planning, and then all the robots go off and execute their tasks. Do you have any thoughts on how do you make that more adaptive to have the team sort of adjust the plan allocations if something unexpected happens?
That's a great question, Seth. So part of why I've kind of built the system towards that is that we really wanted to tease out, kind of remove all the other sources of uncertainty. However, a very interesting future path towards to this research is what happens when suddenly the tasks are coming in online, right? So like you're executing a victim rescue task, and then suddenly there is another victim or another hazard that you have to collect somewhere else, right? So the good thing about those plan merging algorithms is that they don't have to be executed offline like this. You can use those plan merging algorithms to say, let's say a new victim task came up, and now you have generated a plan for rescuing that other victim. Now you can merge that existing plan with the plan that you're already executing, and just bring them together. So you can actually adapt this framework with actually very little modification to tackle online tasks. So like tasks are coming online, and you're dynamically incorporating them into the tasks that you already began executing. So that would be a very, very interesting future research.
So you're saying that if you have a task that you already have a plan for, you could bypass sort of the need to do the exact planning and just use your task merging framework to just merge that plan again into itself? Yeah.
So the good thing about the plan merging algorithms is that it really doesn't matter where these plans came from, right? So the experiments that I performed, I had a very controlled environment because I really wanted to tease out the benefits of those individual plan merging algorithms. However, if you have different sources for planning, so for example, you can have a person manually building a plan, and then you want to merge this plan with some other automatically generated plans. The merging algorithms will see all those plans as the same thing. It doesn't matter for the merging algorithms. And it doesn't matter when those plans were generated. Only it matters is that those plans were generated separately. And so you can use this merging algorithm to coordinate plans that were generated from people and plans that were generated from robots, or different types of robots or different types of algorithms. So they can help with that as well.
So about how long would it take for your algorithm to merge to like plans?
Yeah, so that's a good question. So that also depends on how complex and how detailed your model is, right? So in the deployed robots, our plans usually took less than 5 minutes to synthesize because we had just 4 tasks and just 6 robots. Now in the simulated experiments, we really wanted to push the boundaries. So we really we had many more tasks and many more robots. And as you saw, once we got past say 8 to 10 tasks in that particular complex domain, we kind of reached the ceiling. But depending on the level in which you're operating, you can generate very, very quickly, such as in the actual deployed robots that we experimented with.
Can you clarify what you mean by a ceiling in this context?
I see. So the ceiling, I mean, is the boundary that we're trying to push, right? So we're not happy with just playing with the small number of tasks that we know they will execute fast, but we're also trying to push the boundaries and see, well, what happens if we double the number of tasks? So we pushed the boundaries and we stretched out to see how far we can go. And that ceiling was around 10 tasks for this particular type of domain complexity with the features that we incorporated. Now it gets significantly faster as you have the number of tasks. It can be a matter of seconds to a few minutes to more, depending on how complex you model your problem.
Right, thanks.
Anyone else? Seeing no hands, are there any questions from the committee they want to ask before we dismiss everyone else? Seeing no one turning on their microphones, we'll ask everyone but the committee to please leave the meeting. Thank you for attending.
Thank you.